Okay, so you have looked at both of these forms, yeah?
Yes.
And you've looked at the graph, and now what I'm after is for you to tell me what you can determine either from the equation to know about the line or from the line to know about the equation. So what have you found out? Go.
Oh.
Tatum.
The C is the y-intercept.
Okay, so this value here will give you the y-axis intercept, right? That would be here at this bit. So this would be the C value.
The higher you make the exponent, the more...
I'm not after you. I asked you specifically to look at quadratics. I know you went in to look at higher exponents, but I wanted only quadratics, x to the power 2 maximum.
Okay.
Yeah.
A is the gradient.
A affects the gradient, or when you say is the gradient,
It affects the gradient.
it affects the gradient. So it's not quite the same as saying with a linear function m is the gradient. A will affect the gradient. Yeah?
B affects the vertex, and then also, but that would also affect the y-intercept too.
Does it?
Actually, no, it doesn't.
Doesn't, does it?
No, it doesn't.
So A does affect the gradient of the line. But what do we know about the gradient of a curve?
Of a curve?
Yeah. So I did with my M3s, therefore you must have done it. We did stuff about linear relationships. Now linear relationships would produce a graph. If we were to graph that relationship, that shows a constant relationship between two, a constant change. And you have done that this term, or was it the end of last term? What kind of relationship have you studied that is also linear?
Never mind.
You did it in one of your homework sheets as well. It wasn't linear, that one, but...
Was this that one with like the lines and the diamond pattern?
That's not, no, it's not what I'm thinking of. Everything in maths is linked in so many more ways, and I find sometimes people think maths is huge and there's so many things you have to know, but actually most of it is just different ways of expressing the same thing. So a linear relationship, we have looked at direct proportionality, right?
Yeah.
As one thing changes, it creates a change in the other, but the relationship is always the same. That relationship would be shown by which parameter in direct proportion? Which letter did we look at? Have to work out.
K.
K. K shows the relationship, yeah? So if we had y is directly proportional to x, we would have y equals kx, yeah? K being what we multiply by. Now you've also looked at y equals mx, where m is the slope. Well, that's the same thing, yeah? K and m, same thing. We also then looked at, when we were doing direct proportionality, other relationships that weren't linear, such as what if y is directly proportional to x squared? That would look like this, wouldn't it? So if I look at y is directly proportional to x squared, if I were to graph that, I would get this curved shape. But I'm now adding other components as well. All right? So it's all linked. Now you've noticed that if I change this parameter a, it does affect the shape of my quadratic, yes? Right? It changes the gradient. But what do we know about the gradient of a curve? I'll go back to that again. So if a linear relationship is a constant relationship, a curve is?
Constantly changing.
It's changing. Yeah, the relationship is changing, right? So the gradient here is what? Positive or negative?
Positive.
No.
Negative.
Negative, because if I drew a straight line, it would be going down, negative gradient, yeah? Gradient over here would be?
Positive.
Positive. The gradient down here would be? Negative. And by the way, you've just done pre-calculus.
Yeah.
calculus is all about gradient of lines, gradients of curves, and working out equations that work that out. So talking about knowing that this is a negative gradient, this is a positive gradient, and this is a zero gradient. What do I know about the gradient here compared to the gradient here?
The higher one's more negative?
Yeah, okay. So what has happened to the change? What's happening? Is the gradient increasing or decreasing? Increasing, isn't it?
Because going from negative to 5.
Exactly. Going from highly negative to not quite as negative to 0 to positive. It must be increasing. So we have a changing gradient. So we can't say A is the gradient, but we can say A has an impact on the gradient, can't we? So what did you notice? As A is larger, what? As A has a higher value, what happens to the shape of the curve?
It becomes narrower.
Becomes narrower, yeah? So we increase each of the gradients increases, yeah?
Yeah, that's what I was trying to say with the exponents, but
Oh,
it's
okay.
actually the A that makes it narrower.
Do you understand why we're not talking
Yeah,
exponents?
yeah,
Okay.
I didn't.
Cool. Right, but is there any way of looking at it and going, well, if A is 5, I know the gradient is, or was that just a, if I change A, I know I've got a narrower? Yeah. So if I had to model a situation and I wanted a curve, think back to why we're doing this. Why are we looking at shapes and quadratics again? How did I introduce it 2 lessons ago?
Like real life examples, like
Yeah.
motorbikes.
Yeah, and what kind of motion?
Parabola.
Yeah, a parabola shows a certain type of motion. Begins with P.
Parabolic.
That's the shape, but what kind of motion? Begins with P.
Parabola.
He said that the shape is a parabola, but I'm looking at projectile motion. If I throw something or kick something, or the bike guy gets, you know, this, when it's this way up though, it's not really a projectile as such, is it? But so we would, how would we get it the other way up then? Yeah.
You make A positive because, well, here it's negative. Because, alright, we'll give it to someone else.
Why?
Because I can't answer this on that.
Well, you just had an attempt. You were almost right. But you said in this one A is negative, but actually in this one A is
Positive.
And how do I make it the other way up?
By making a negative.
By making a negative. So most of your projectile motion ones will have a negative A. So having the curve up the other way, like this. Oh, really bad drawing there. A would be negative in this case, and this one A would be positive. So we know about the shape. Nick?
I mean, this question's related, but it's just like something I've kind of always wondered with like graph lines like this. How do you know, like the blue parabola? How do you know, like, why is that side negative? You know what I mean? Like, yeah, I know it's like.
What do you mean?
The line's going down, but like.
The gradient being negative.
Yeah.
Because if you think of gradient as a rate of change,
Yeah.
so what this means is if I take, we've talked about this before, if I take a point on a line, what does that represent? Greg?
That point represents where x is like say -5 and y is 4.
You're still talking, you're correct, but you're still talking in abstract
okay.
amounts. But yeah, go on.
So that point designates where, x squared equals, no.
I'm not even after that.
Yeah.
I'm asking that. What is a line again?
A series of points.
A series of points, an infinite number of points. So every point is a, then we look at every point is a moment in time or whatever I'm measuring. So I'm looking at a relationship between what and what in this case?
You could say
Make one up.
yo-yo height and time.
Height and time, okay? I'm looking at a relationship between height and time. Right, Nick? So this point here is a moment in time where I know that at this time, the yo-yo is at this height. It's a point in time, yeah? So if this is time, time has to go in this direction, yeah? And this is what we look at. Normally for the x-axis, we go left to right. So what is happening to the y variable? So on this time, I have gone from here down to here, yeah? So what has happened to the y variable? It's decreased. So an increase in x variable has provoked an decrease. All right? So is that a positive or a negative relationship?
Negative.
And how would that be? How could you connect that to your scatter plots? It's not actually.
No correlations, like, negative direction, positive
So
direction.
negative correlation, yeah? But we only talk correlation when it's not an exact, it's not a straight line. It's not inversely proportional. Or is it? Is it inversely proportional? Or
Because isn't inversely proportional where one goes up, the other goes down?
yeah.
Oh wait, but it's not, like, it doesn't go down.
It's not like that forever.
Like that curve.
It's not
Exactly.
even a linear proportion in the first place.
Yeah.
It's non-linear.
So, but what we're looking at is to say, what is the relationship? Now, this has a negative gradient because as x increases, it's provoking a decrease or a negative impact on the y. If I go over to here, if I go from this point and then go in the x still in that direction and go up there, what has happened to the y variable now? It's increased. Therefore, I have a positive impact or a positive gradient. Yeah.
How do you know, though, like I understand that, but like how do you know that the line starts on the left side? Like what if it started on the right? And say it wasn't time, because obviously you can't go backwards, but say it was a different variable where...
But we go left to right. It's like, how do you say I look at a book and know which direction to read?
So you can't, I guess I'm nursing a graph like that. So.
Yeah, we tend to just read in one direction, don't we? In fact, with graphs and things, you can read in any direction you like to take values, but when we talk about a relationship, when we talk about when one thing increases, the other one increases or decreases, that's what we look. We go, take your what variable is it? Someone had it in their piece of work. Which variable, how would we describe the x-axis variable?
The independent variable.
The independent variable. I think the person did it the wrong way around in their work. The independent variable is the x-axis, isn't it?
Yes.
So you take that variable and it's what, if I increase my independent variable, what does it provoke in my dependent one? Does it make it increase or decrease? All right. So it just depends how long my graph is. Anyway, back to the quadratics. So A does affect the gradient, but it doesn't tell me specifically anything about, like for instance, if I told you y equals 5x squared, would you be able to just go, yeah, I know where that goes? But if I said to you, it's 5x squared plus 3, could you tell me something about the graph?
Yes.
It crosses the y-axis at 3, yeah? So we've got this piece of information here. This is very useful. In our general form, we can find our y-axis intercept. All right. What about factorized form? Does that tell us any more?
It tells us less because we don't know the y-intercept because it's
Okay,
factorized.
but
Unless you just multiply A and B.
Oh, yeah, but just from looking at the form, you don't know the y-intercept.
so does that not tell us anything?
Yeah, it tells you stuff, I think.
What?
I don't know.
Not that much.
Well, it tells you the
Tells you an awful lot, actually.
it tells you the A and the B.
Those A and B's are different, aren't they? Because remember, we have to multiply it out. Sorry, maybe I shouldn't have used the A's and B's. So, for instance, if I draw another one like this.
Oh, it tells you one y-coordinate and an x-coordinate, right?
Oh, wait,
Is it?
because if you put 1 to 0, you can find out what one
Oh,
of them
the other
is.
one is.
Okay, so what does that tell you in terms of the graph?
So it tells you that the A and the B in that situation is x and y. Is A, x, and y. Never mind.
Tell.
That they are.
This form is very useful if we put it equal to 0.
Yes, because then you can figure out what the.
These are.
Yeah, because like if x was 4.
Let's say these are the A and B. Minus A and minus B. So, for instance, if I've got x plus 2 and x minus 8, all right, if this is the form of the equation, I now know that my graph will cross at -2 and +8. So factorized form tells me my x-axis intercepts.
Oh, that's.
Okay? So that's very useful.
Wait, so technically all you need are the x-axis intercept and the y-intercept.
No, we need one other thing, which was?
Slowing.
No, we're not actually working out gradient yet, not until we get onto calculus, which will be next year. So what else was the other thing that you were asked to look at? It wasn't actually a form of the equation as such, but it was...
Oh, the move, the
Translation.
Symmetry.
the axis of symmetry. What was the formula for the axis of symmetry?
Dang it.
Too much chatting.
It's the vertex, so it's B.
It's the it helps you find the vertex, doesn't it?
Oh.
So the axis of symmetry is halfway between, my numbers are not very good here, but the axis of symmetry would be in the middle, right? So I shouldn't have done that. And the vertex lies on the axis of symmetry.
Surely you can't just do 2 plus 8 and then divide that by 2, right?
That is another way, isn't it?
Okay.
This value here would be, would it be the mean of those two?
I mean, yeah.
So if I did x bar just to represent that, so that would be in the middle.
Yeah, that'd be 3,
Right?
right?
It's another way of doing it. So again, my factorized form is another way of finding the x coordinate of the vertex.
Okay.
Nick?
What if it was a sideways parabola?
What?
Like,
Oh, like this?
Oh,
Like,
the half
yeah, like that.
like if it,
Then the
It's not a quadratic function, but any idea what
Yeah.
function it would be?
Isn't it like
That's
that?
not-
It
cubic.
actually wouldn't be a function. We talked about
Yeah,
that.
it's not
It's
function.
like the one thing.
It's a
Wait, why
long-
can't that be a quadratic form?
A quadratic function will look like this. If you put it...
I know, but then if you translated it, like rotated it.
Okay, but what? It's not a rotation, is it? We did functions. Do you remember doing inverse functions?
oh, yeah.
What's the relationship between a function and its inverse function?
They're in.
But what about the graph? What's the relationship between the graphs? Ethan?
Isn't it reflected across x and y?
Yes, reflected in y equals x. So what is the inverse of x squared?
X cubed, the X rooted, root X.
Root of x. Is the root of x a function?
No,
Because it fails the
rational test.
Vertical line
the
test.
vertical line test. Yes, so that is what you would have. You would have a line, if you draw that, all right,
And then
it is a reflection in y equals x, but it's the y equals root x, and it's not actually a function.
'cause if you
Yes,
put a
Ethan.
line to
Yeah,
the
This is just a basic math question. The
Yeah.
vertex is the middle point.
The vertex is also known as either the minimum or the maximum. So in this case, the vertex is the minimum y value, which also, if you remember, is the, in this case, the lower limit of the what? Do you want to answer that question, or you got different? What is the vertex, the y coordinate of the vertex? What is it the lower limit
Oh, we
of?
did this ages ago.
We did.
Oh,
The minimum y value.
Oh, that means that is the smallest possible y value.
Which is the lower
we did
limit
this so
of
long
the
ago.
what of the function.
The
Inverse.
symmetry.
No. God, I
X value
remember.
of the function.
It's in my old book. I know
The
it's
y
in my
value,
book.
so the minimum y value is the lowest limit of the what of the function?
Because there's a limit and there's a top limit and there's a left and the right limit, but what is it called?
Range?
Yes!
Oh, yeah.
The minimum is the lowest limit of the range, okay? The range of the function. Yes?
Why is a function defined to like having to succeed the vertical line test? Like why?
Because, again, it goes back to thinking about computers is the way I like to think about it. So, computers are stupid. They take one input and give you an output, yeah?
Yeah.
They can have ifs and but statements, but basically you have an input, you have an output. How do you make the light come on in your room?
I click the
Press the
switch.
button,
Yeah.
right? Can you program a computer, even the most complex computer, to, when you press the light button, for either or button, light to come on?
Oh,
What do you
no.
mean either?
No. It will either do one of the lights, or it can do both of the lights, but it can't choose one or the other, can it?
What if you,
Why not-
what about a random?
Yeah.
Okay, well, randomly is not choosing the one that you want to happen. So, for instance, if I walk into a room and say, there's two lights in there, and let's even talk up to date. Alexa, turn my light on. Which one would she put on?
None of them are all of them.
None of them
Or
or all
should
of
say
them.
coming in.
Or you can specify extra things and say, Alexa, turn the light on in whichever room.
Smartphones.
All right? But you can't say, Alexa, turn on the light and expect her to know which one you want to turn on. Because she has an input from you, and your one input must have one output. You can program to say, Alexa, turn on the light. Alexa, switch on the light. Alexa, illuminate the light. There are many ways of getting one thing,
Yeah.
many to one. I can't, however, have a
One to many.
one to many. She does not work.
Yeah.
Yeah?
Those little like line drawing lines.
There has to be a computer that can like have
No.
human feelings and human.
That's called art.
That's
That's
called human.
It's called Hollywood.
It's called a human.
Oh yeah.
Artificial intelligence, that is the sign of intelligence, when something can interpret and make a choice, and we don't have that
I'm
yet.
sure there's a computer that can make a choice.
Yeah, it's called a human, Nick.
Yes, but it can't interpret your wishes. It can make a choice, it can't interpret your wishes.
Yeah.
Is what I'm saying.
No machine has free will.
So when we have a function like this, the one-to-many thing means if I have one input, I need to know what one output will be. If there's two possibilities, we can have it, but we can graph it and we can do all that, but we don't call it a function. So, before Nick packs up everything, because I've got like a minute and a half to go, I want you to be able to identify using standard form, axis, the factorized form and the axis of symmetry. If I said to you, here is an equation, I should be able to give it to you in standard form or factorized form. You should be able to identify how many points on the curve. How many?
One,
Nope.
2,
3, 5,
6.
7.
4.
4. Finally. The two x-axis intercepts, the y-axis intercept, and the
Vertex.
vertex. 4 points. We'll try it next week.
All right.
Have a good